When you look at a steep hillside, you're actually seeing a silent, invisible battle. On one side, you've got gravity, just relentlessly pulling everything down. And on the other, you have the hidden strength of the soil itself. Now, most of the time, the soil wins. But what happens when it doesn't? That is the question, isn't it? And it's one that keeps a lot of civil engineers up at night. Because when a slope gives way, it is never random. It's pure physics. A total breakdown of things like pressure, friction, and water. And learning how to read those signs, well, that's the key to preventing a disaster. So, for this, our story takes us to the Western Ghats in India. Just picture it. You've got these incredibly steep, towering slopes, and they get absolutely hammered by some of the most intense monsoon rains on the entire planet. It's basically the ultimate stress test for the ground right beneath our feet. All right, so first, let's really dig into the problem itself, because a failing slope isn't just some random act of nature. It's a direct threat to our roads, our homes, and yeah, our lives. Think about it. Every single road that's carved through a hilly area, every house that's built on a beautiful slope, all of it relies on one simple thing: the ground staying put. And when it doesn't, it's not just an inconvenience. It threatens people's lives. And it goes right against these big global goals for building safe, resilient communities. This is where engineering becomes, quite literally, a life-saving science. So, how in the world do you diagnose a dangerous slope? You can't just look at it and guess. No, engineers have to become like geological detectives, digging deep to uncover the secrets that are hidden right there in the soil. And the process is incredibly methodical. It's really cool. First, the engineers go out and they identify the slopes that look potentially unstable. Next, they collect soil samples, and they get both disturbed and undisturbed samples to make sure they're preserving the natural structure. And then finally, all of that gets taken back to the lab for a super detailed analysis. Now, they're looking for two crucial properties. The first one is called cohesion. The easiest way to think about this is as the soil's natural glue. It's that inherent stickiness that holds all the little particles together. So clay, for example, has tons of cohesion. Sand, on the other hand, has almost none. Okay, so the second key property is the angle of internal friction. Now, if cohesion is the soil's glue, this is its grip. It's all about the resistance that comes from all those tiny soil particles rubbing against each other. Just imagine trying to slide two pieces of sandpaper past one another. It's tough, right? That resistance is friction, and it's a huge, huge source of a slope's strength. So once the engineers have these two values, the glue and the grip, they can do something pretty amazing. They can take all of that complex data and distill it all down to a single critical number, a number that tells them if a slope is safe or if it's right on the verge of collapse. And that number is called the factor of safety, or FOS for short. At its core, it's actually a pretty simple ratio. You just take all the forces that are holding the slope up, its strength from that cohesion and friction we talked about, and you divide it by the forces that are trying to pull it down, which, let's be honest, is mostly gravity. And figuring out what the score means is really straightforward. If the forces holding it up are way bigger than the forces pulling it down, you get a high factor of safety. So anything over 1.5 is generally considered safe. You're good to go. But if that score drops below 1.0, that means gravity is winning the battle. The slope is failing. So here are the actual results from those three sites in the Western Ghats. And wow, just look at these numbers. Bettagere comes in at 1.14, Beranagodu at 1.15, and Kesavinamane at 1.13. All of them are hovering dangerously close to that 1.0 failure point. So the verdict here is crystal clear. These slopes are absolutely not safe. Yeah, they haven't collapsed yet, but they are only marginally stable. One heavy monsoon rain, maybe a minor earthquake, that's all it could take to push them right over the edge. They're basically a ticking time bomb. But identifying a problem is only half the job. Now comes the really clever part: engineering a solution. How do you actually strengthen an entire hillside from the inside out? Well, engineers have a whole toolkit for this kind of thing. They can do things like build retaining walls, or they can use more advanced techniques like soil nailing, which is literally like stitching the slope together with huge steel bars, or driving these deep foundations called piles into the ground to act like internal support columns. So the engineers in the report then modeled these solutions to see what would happen. And the results, they're incredible. Let's just look at the Bettagere site. Before, the factor of safety was a really dangerous 1.14. But after they modeled adding soil nailing, look at that. It jumps to 1.83. And with piles, it soars to over 2.1. That is a massive improvement. This chart really shows you the whole transformation. You go from a critically unstable slope, something in the red zone, to one that's robustly safe, deep in the green. That right there, that's the power of geotechnical engineering, turning a really high-risk situation into a secure one. So why does this one project in India matter to all of us? Well, it's because this exact process, investigate, diagnose, and stabilize, is the blueprint engineers use everywhere to protect communities. From the highways in the Alps to the railways in the Andes, this is the science that's keeping us safe. The big takeaway from all of this is that the best, most effective solutions always come from combining that hands-on, site-specific soil testing with really powerful computer analysis. That's the secret sauce. It's how engineers develop fixes that aren't just effective, but are also affordable and sustainable for the long run. It really makes you think, doesn't it? We've just seen how engineers can predict and prevent something as powerful and as immense as a landslide. So what other invisible forces are they helping to protect us from every day? And what other hidden risks can we solve just by looking right beneath the surface?